Okay, so I think it's time to start. Hello, everybody. My name is Yury Zaytsev. I work at Jülich Forschungszentrum, and I've had the honor to be invited today for this Python tutorial. It was supposed to be an interactive one. I might be maybe the one to interact most, but feel free to interrupt me at any time. I guess you have to be loud because I'm a bit on the deaf side, but at least I'll try to be loud. Feel free to just, wave your hand and ask questions. And if it's too long, then we can postpone it. Okay, so as I said, I'm working at the research center Jülich at the supercomputing center. More specifically in simulation lab neuroscience, and it's pretty much what it says. So I'm doing mostly simulations, some data analysis, and the institution is famous for having the biggest supercomputer or the biggest machine in Europe, which was the case until last year in Switzerland. They bought an even bigger one, so we had urgently to dismantle all science. That said, we are the first. But anyways, it's still pretty big. They call it UQueen. It's IBM Blue Gene Q. For those who are not familiar, it's not with supercomputers. It's not exactly like your laptop. So it's a power architecture, very strange proprietary modification of Linux kernel interface only through the batch queue and so on. And yeah, I'm running my stuff there, among others. And this machine is quite big, computes quite a lot of power. So you might guess where my interest for profiling and performance come from. And having that said, the next question to discuss is why in the world I did put the responsible in the subtitle. So the reason for it is that one doesn't just go ahead and optimize the code. And this is something that I call drive-by optimization. And by that, I mean something that occurs to me on the daily basis, especially. I don't know how true that is for engineering or industry, but in scientific domain, you always have some code, and then it doesn't run fast enough. Something is slow, it consumes too much memory, and then the author comes up and says, oh, thinking more clearly, it's obviously this line that is at fault, and I replace this algorithm with another one, and it's going to work. And then he does so, and a week later, it's even worse. And then he says, oh, but in retrospect, it's clear that it's that other line. And now that I replace that, it's certainly going to fly. And then next week comes by, and we are still where we started. So that's why when you try to optimize your stuff, you should first answer two questions. So one is how much exactly of resource of interest is being used and how these resources are being spent. And X is somehow usually implicitly assumed to be CPU time, but it doesn't have to be. So it can be anything that is of value for you. It can be RAM, it can be input-output bandwidth, can be network, can be power also, especially for big machines. It takes as much electricity as power in a small suburb town for a day, so you might be concerned about that as well. So profile the code to find answers to these questions and thereby engage in responsible optimization. So obviously, the act of profiling is looking for bottlenecks, and why it warrants to have a tutorial on that is because actually things have become so complex that you can't just do some hand-waving analysis or test runs with some custom timing code on pen and paper. So right now you have hardware, which is mostly your CPU and memory, and then it's connected to the memory via the memory bus. You have an I/O bus that connects it to this controller or network, and this whole thing is managed by something called operating system. The bigger part of it is a kernel that provides a layer on top of all these hardware resources, and you don't usually see directly the hardware. Usually you are worried about things like pages, memory pages, or I/O inodes, and so on and so forth. And so this thing manages these resources, then it exposes them to system libraries, and only there at the top you have applications where your code is running. Finding the bottlenecks is not as easy as it used to be, and it involves often system level profiling and also application profiling. So, however, in this particular talk, we're only going to concentrate on this kind of thing. So only this upper part where your applications are running. And maybe this will give you a sense, now that I only covered this, how much it would take to cover the whole scheme. So I took this picture from this website. It's run by Brendan Gregg, who is an engineer at Netflix now. And I really encourage you, when you have time later, to have a look at his website. As not so long ago, he released a book on systems profiling. And so this upper part is basically not very much covered there at all, but the rest of it is. So my plan for today is first to give you an overview of the things that are available on the market, because I really feel like having a classification in your head helps to select the right tools for the job. It also tells you in which direction you should be looking, where you want to find something else when the tool that you know are not able to solve your problem. And then we'll try to apply it to some practical examples, and I will conclude with a summary. Right. So having this said, let's look at the classification of profilers that I came up with. So this is, not something that there is no ultimate theory of profiling. I just came up with it myself, but I think it's sensible. So first, you classify them by the kind of resource that you are profiling. Can be CPU, RAM, bandwidth, as I said already, and then the way it is profiled. And here I want to emphasize there are two classes of tools, or broad classes of tools, that are deterministic and statistical profilers. So the deterministic tools basically take your code instruction at a time and then attach some extra to it that measures the resources of interest and records this data. And it does it to every single instruction. It's great because it provides you with precise information of what's going on. You can gain many valuable insights this way. However, it has a drawback that it is slow and often it produces a huge amount of data. So there is another class of tools that are called statistical profilers. These are not always as precise, not always that granular, but they are fast as a rule. And especially if you are working on large scale, you might prefer them because they produce a manageable amount of data, so which we will discuss later in a moment. And then there is also the question of granularity at which you are looking at the code. And the scheme that I presented a couple of slides ago basically showed you the application level, but then when you go deeper, you can look at the individual functions. That would be method level, and then it might turn out that actually this is not enough, and then you have to go really to the line level or the level of individual instructions. And then there is a question of how it is reported. So most of these tools just generate data files or print some strange summary that you have to interpret in a way or another. There are many visualization tools. I try to make a point that they are useful. And then you can see already that, I mean, there are pretty huge amount of combinations already so far. So I will not be able to cover everything, but hopefully this will be enough to get you started. And if you are really interested in them, you can go deeper. So in what concerns the profilers for Python specifically, first thing that I'd like to mention is something I call snippet level profiler, or TimeIt. It's part of the standard library, and I encourage every single person in this room to use that instead of the handmade decorators that import the time module and register the timestamps. So there is a reason why this is a big module and why it is in a standard library. The reason is that lots of smart people put their work into it. It's not trivial to get it right. It uses high precision counters to measure the CPU time. It tries quite hard to isolate the results from the interference caused by the outside world. It tried to do statistics right and so on and so forth. So please use it. This sounds trivial as an advice, but we'll see later, I hope, that it really makes sense. And then there are method level profilers. The deterministic one of choice would be cprofile. It's a former LSProf for those who remember the early days. It implements exactly the same interface as profile, which is a pure Python profiler. And the latter is basically slower and only useful to find bugs in cprofile itself, which are not many left by now. So I don't know. I'm just mentioning it because it exists. And then there was another experimental profiler, Hotshot. Unfortunately, it's dead in a sense that it has been removed from the standard library in Python 3. So might not make much sense to spend time on getting into it. So then there is statistical profiler StatProf by Brian O'Sullivan. There is a line profiler by Robert Kern that works on the line level. And in terms of memory, the tool of choice, we have something called memory profiler, which is, in terms of user interface, very similar to line profiler. And then there are other tools like Guppy and Hippie. So Guppy is actually a whole framework for constructing memory profiling tools. And Hippie is a Python stack profiler, Python heap profiler that is implemented on top of this framework. Unfortunately, it's Python 2 only, at least at the moment. And then the other one, Pimpler, works both for Python 2 and 3. But these guys are quite advanced. And unfortunately, I don't think we're going to go into it today. But you have to know that they exist. So this kind of tools are mostly useful when you are one of those crazy people using Vic references directly to circumvent, you know, this garbage collection cycles thing. So, and then of course you create memory leaks, and then you have to track them down. And then you would turn to these tools. But I hope I'll show something else instead that is more practical for most purposes. And then if you are interested in Python performance, obviously you are using Python extensions. And one extension of choice would be, of course, NumPy, which provides highly optimized code for n-dimensional arrays. And these extensions, or the core of them, are implemented usually in compiled languages like C or C++ or Fortran. And you won't see much using cprofile on these extensions. So at this point, you just have to use the corresponding profilers for the languages that are used to write these binary extensions. So I can mention gprof, perf tools by Google. There is a number of commercial options like Intel VTune Analyzer. But if you are, you know, interested in this kind of thing, you are probably, I mean, you don't need me to be telling about that. And then there is generic and conversely special purpose profilers. So something trivial that I will mention at the application level try to make a point that actually it's surprisingly useful, is just a time command from POSIX standard. It's available on every single system that makes sense. There is perf, the interface that exposes Python, Linux performance counters. You can do dynamic analysis with Valgrind. Valgrind is a framework for implemented dynamic analysis tools for performance analysis and correctness checking. Specific tools of choice are CoGrind, which is a method level profiler, and KCashGrant that is more geared towards finding out how efficiently you are using the cache lines of the CPU, how many faults you have, and things like that. And Massive, the memory analyzer. Then there is a bunch of tools that are specific to high performance computing. But again, probably if you are doing this kind of things, you know them better than I do. So there is something called Puppy that is very useful, performance API. There is ScoreP for measurement. It has all kinds of collectors that can be useful, and then the usual analysis tools. So in this talk, I will cover of these ones. And hopefully, I will be able to make the point that Valgrind is not halfway as scary as it seems to be. So let's get now. Yeah, I think that's enough for the introduction. So, and I'm happy to switch to the practical examples now. And probably after that, you're going to start having questions. So something that I'd like to start with are this classical benchmarks of choice, the Fibonacci numbers. So just to remind you, this is a sequence of numbers where each next number is the sum of the previous two numbers. And the goal is to find the nth number. You can obviously do this in two ways. So first way is just make a loop, as in Fib1Pi. You start with 0 and 1, the first two numbers, and then you iteratively use these previous numbers to compute the next one and return it. Or you can implement directly the mathematical formulation. So you can say that for any number bigger than 1, it's the sum of the previous two numbers. So fib of n minus 1 minus 2. And otherwise, it just returns what you've been given, which would be 0 and 1. And this function is not defined for negative numbers or floats and so on. So any ideas already which implementation is faster? Just shout. I mean, I don't know. The first one? Yes. Well, I mean, let's have a look. So yes, of course, the first one is faster. And this is how I use timeit to prove it. One thing that not everybody knows is this very convenient way of invoking Python interpreter with -m switch. So basically, you can make Python import a module that you are asking on the command line before it actually runs your commands. And modules can be coded in such a way that they will detect that and do useful things for you. And timeit in particular is one such module. So you have to invoke Python with -m timeit. -s is the command line argument provided by timeit. It's setup code that is run at the beginning of the benchmark. And then you have to provide the code that you want to benchmark, which is in my case the 31st number of Fibonacci computed. Then it does its magic, and it tells you that it took 3 microseconds per loop. The second kind of function takes 3 orders of magnitude more time. And even I had to give this -n3 switch, which tells it how many loops it should perform to do the timings. Because if it tried to do as much loops, we would have I would have never gotten this result in the first place. So so much for that. The question is, can this version, which is obviously incredibly slow, be improved? So do you know what the major problem could be with that?
Recursion.
Well, recursion by itself is not a problem, right? Yeah.
Repeated calls. So when you do fib of n minus 1, you'll be doing fib of n minus 2 as a part of that.
Yeah. Yeah, exactly. So basically, you are just computing things that you have already computed over and over again. And I mean, of course, recursion is bad enough, but then you also recomputing things all the time and throwing them away, which is stupid. So what you could do is a bit of, I don't know, Haskell-like stuff. So you can create a dictionary, and in this dictionary, store the first two numbers. That's what you use for initialization. And then if this number has been computed already, you just return it from the dictionary. And if this number hasn't been computed, then you compute it using this recursive way. So, yes?
Your function is no more Zaytsev in this case, which is considered as a bad practice.
So let's time that then. Right. So I would have expected that it is then faster than the previous case. Than the previous recursive version. But who actually believes in the sincerity of this assessment? So not much people, apparently. Okay, so let's see what's actually going on in the first place. So there is a -v key that timeit recognizes, and it stands for Verbs. In this Verbs mode, it prints more things about how it is actually measuring your things. And as you can see here, it starts with 10 loops, and then it tries to understand how fast or slow your function is in the first place. And then if it realizes that your function is too fast, then it will increase the number of loops automatically so that it can suppress the interference that happens due to other running processes and so on and so forth. And so it does 10 loops. It realizes that it takes this much seconds. And the interesting part, you can see that they are, pretty much the same number for these two versions. And then, of course, it does 100 loops, and it's 10 times slower. In this case, it does 100 loops, and it's 100 times faster. And so then it does more loops, and then it comes up with this great result. And what is happening here, actually, is the function is indeed not stateless anymore. And what you are doing, you are measuring here the dictionary access time in Python. So another thing that timeit is useful for, you can test small snippets very easily. And so here I create a dictionary that has 901 keys, and then I create a function that looks up things in the dictionary. And the reason why I do this in such a stupid way is because I want to make these test cases similar, so comparable. So I replicate the infrastructure that is not needed. And if I measure this, then I get 300 microseconds per loop. So congratulations, we have here identified how much time it takes to look up things in the dictionary that is not very full. So the conclusion from that, I would say, is, of course, you are much safer than ever before. Than ever when you have been using your hand-coded decorators to measure things when you are using timeit, but you still have to think about what you are measuring. So in this case, for example, you are measuring really just the dictionary access time and not the time it takes to compute the function. So be careful anyways, and doubt your results. And then the other question is, of course, can we make this even faster than that? Any ideas? Yeah, just say it.
Hardcode the solution to the differential equation?
Yeah, so there is, as to any series with linear coefficients, there is just a closed form solution. So in order to compute the nth number of Fibonacci, you don't actually have to compute all the previous ones. You can, by virtue of pen and paper, derive the formula that directly gives you the nth number. And so that is a matter of just computing this coefficient and then computing this phi to the power of n minus phi to the power of minus n, dividing it by the magic square root of 5, and you're done. So if you benchmark this, you will see that this solution is 6 times faster than the fastest version that we had so far. With one caveat, however, so this number 70, I haven't chosen it. I have chosen it for a reason, and the reason is if you do this for 70 and 80 with the first version, you will see that these ones match. These ones are actually different, and the point is this formula is correct, but it requires floating point numerical precision that goes beyond the doubles that I used in Python, and therefore when you round it as an integer, you get a wrong result. So this formula is actually only applicable up to 70, which is why I have used that in my benchmark. Right. So the conclusion is, I mean, you really have to know what you are doing, and when you are testing different things, which one is faster, you also have to see if they do the same thing. So maybe another solution is faster or much faster, but wrong. And then the question is, do you really need a wrong solution, or you need the correct one, albeit slower? Right. So that was the introduction. I hope, well, by now you might have gotten the idea that I will go ahead and then apply every single profiler to these amazing examples. So my strategy is somehow different. So what I'm going to do, I'll take a real problem that hopefully can be explained rather quickly from something that we really had to do in practice. Therefore, you might have seen this already. So those who know exactly this example, please do not spoil things. And I will, of course, do the proper attributions at the end. So what we're going to do is bootstrapping. And bootstrapping is this kind of thing. So this is a figure from a paper that appeared at the beginning of the year in Nature. It says they localized sources of water vapor on a planet near Mars. Everybody was very excited about that. And the question is what actually makes us believe all these things. And what makes us believe these things are these little guys here. So these are the markers that show the measurement errors. And they show how confident we can be that the true value is actually somewhere in this region denoted by these markers. And the way you compute these markers, especially for empirically measured data, one way at least is bootstrapping or computation via pivotal quantities. So in this case, I offer this problem. So let's assume that we are also all scientists doing some very important measurements. What we are doing, we are measuring things that are distributed between 0 and 1,000, and the mean is what we are after. So we would like to compute the mean of this measured things. However, we also would like to compute a band. We want to know what is the interval of confidence where the mean lies with 95% probability. And then we can be quite certain, you know, that our measurements show something, or I don't know, in particular, indicate there is life on Mars. So one simple implementation in Python would be to generate first a large set of fake measurements or X values. Then you try to find the confidence interval, whatever this function does, for the probability of 95%. And you'd like, hopefully, to do this in minimum iterations. You increase the number of iterations that you are doing if the variance is above the threshold in several consecutive trials. Otherwise, you just accept one of the confidence intervals that you have computed. And then you profit from your work. So the code comes in a minute, as I said. But first, let's try to see if we can analyze this program as a black box. So to do that, I would use the time function that I mentioned earlier from POSIX and this -p thing. basically it tells it to print time in standard format, which would be seconds. So I then run through time command the Python interpreter with a confidence pi file, which is the script that computes the confidence interval, and then it prints the number of iterations and the corresponding variance, and you see that the number of iterations goes up, the variance goes down, and then it's below threshold, so it stops, and it realizes that the mean that we are looking for is 498 for this data set, and it's somewhere, you know, in this interval between 496 and 501, something like that. And it takes quite some time, so 36 seconds. The question is, does everybody in the audience knows exactly what these numbers are? So, I mean, you can just say we all know or we all don't know. I mean, okay, yeah, you know. Yeah, but then you are the only one, so. Perfect. So let's take another example. Probably most of you have nothing to do with neuroscience. That's why Nest doesn't tell anything to you, but let's assume it's an amazing tool that is useful for neural network simulations. And then you do a neural network simulation with a script, which is a standard network in the field, and then you see that it took 55 seconds of real, whatever real is. It took 97 seconds of user, which is whatever user is, and then like less than 1 second of sys. So question is, of course, can this be true? In reality, not. So the trick is that this laptop actually had 2 CPU cores, and this program Nest can take advantage of that. So if it detects that there are multiple cores available to it, it parallelizes the computations. And in this case, it parallelized up to 2 cores. So to recap, real is actually the wall clock time that it takes for the program to run from start to end. Then user is the amount of CPU time that is spent in user mode. And this can be also in threads if your program is capable of multi-threading and if there are multiple CPUs available to it. Sys is the amount of time spent in the kernel. And the kernel means syscalls. And in practice, this is mostly memory allocation or input-output within the process. And this means that a user plus sys tells you how much actual CPU time has consumed, but real doesn't have to be user plus sys. So user can be much more. And then in this particular case, we can see already that this Nest thing, whatever it is, requires probably quite some I/O or memory allocation, so much that it has taken less than a second. I mean, that's quite some time, really. And then, even though I had 2 cores, it basically parallelized with a factor of 1.7 and not 1.99 or 2. So apparently the parallelization in this case is not very efficient. So that might be not necessarily the fault of the program, but it could be that the problem is such that it requires serial steps, and then the other CPUs are just waiting. They can't get any other work done in this period. So my assertion is then that time is actually more useful than it seems to be. By running your program through time, you can immediately make conclusions as to pathological behavior in terms of memory allocations or I/O. So maybe memory allocation not so much, but there are people who run their codes on compute servers or clusters over NFS, a file system that is mounted, and you see high sys, and you don't know what's going on. So it could be that your program is actually opening some directory with 1,000 of files, and it's waiting on NFS to list them. So this results in high sys. This time is wasted for your computations. And so, yeah, I don't know how many times I had to deal with users that had this problem. And really, they could have done their calculations much faster if they paid attention to that. And then also, you can immediately, by rule of thumb, calculate how parallelizable the thing is. OK. But let's do something more interesting now. So still 36 seconds for a confidence interval of, I don't know, 100,000 numbers in 20 iterations. I think that's pretty extreme. Where does this come from? So the problem is I left the handouts that I carefully prepared at the bed and breakfast. However, it wouldn't have worked anyways because there are too many of you. So what I encourage you to do, I hope the wireless is working. You can open this document and then just look at the source code. I think the source code is on the first page and it fits on the single page. So I did it on purpose. There is no preparation needed, really. And so while you are trying to get this file open in your browser, I can skim over the most important functions. And there are really not much of them. So the most important thing that starts the whole measurement is a function called adaptive confidence interval. What this function does, it starts with try iterations equal 10 and computes 5 trials of whatever confidence interval is. Then if the variance among these trials is less than a threshold or the maximum number of iterations are reached, it just declares that the job is done. Otherwise, it exponentially increases the number of iterations that it tries. And then the other function, confidence interval, takes the values as an input, and then it takes iteration samples from these values. It computes the mean of this subsample and sorts the result. And then it returns lower and upper bounds from this list. And then there are some auxiliary functions, 2 of them actually, mean and variance. And these are just not something that is present in the standard library. So I implemented one-liners to compute mean of a list and unbiased variance estimator. So the question is now, like, did everybody get the file open at the screen? Or, I don't know, maybe should I pose the question, did anyone not get it open? And then you can expose yourself. So, I mean, more or less everybody is in then. Yeah. So, okay. So now, for those who have opened the file, tell me what the problem with the code is and get a cookie. So just wave your hand or shout whatever comes to your head. I mean, in connection to the bottlenecks in the code, of course. I mean, you don't really have to examine every single line, but what are your ideas on where this whole time is being spent, this 36 seconds? Yeah?
To the fact that you're increasing exponentially the number of iterations?
I don't, sorry.
To the fact that you're increasing exponentially the number of iterations, the last increase is so big that...
Yeah, well, okay, that makes sense. Yes, I am increasing them, but exactly in the code, what is the operation that consumes the time? Like, is it, I don't know, what it does? Can you point to some line at random and say that's the thing? Yeah?
There is a conditional there. Conditionals are not very nice usually for performance.
Condition.
Conditionals.
Conditionals, yeah, okay. Yeah, I mean, what you are saying makes sense. There is quite some impact on typed loops with conditionals, like while something. Any other ideas?
Printing?
Printing, well, no. I mean, okay, I will accept this suggestion, but it prints 2 lines or 3 lines, so that's not so much. Yeah?
Is the fact that you included in your calculation, so calculating the input values, the random calculation?
Yeah, I mean...
Setting up the variables that you're going to use later. With
okay, so setup of the original data set.
Yes.
Yeah, I mean, why not? So, okay, come on, people.
Nested for loops.
Nested for loops, which ones?
Specifically the 2 inside confidence intervals.
Yeah.
Comprehension.
Yeah, okay. yeah, so, okay, I think that's enough options, unless you have more. So let's see what it is actually. So to find out, I would use cprofile, and again, I will use it in exactly the same way as timeit. So I will run Python with -m cprofile, and then I will run a script through that. -s in this case means the sorting order of the output, and I say sorted by the cumulative time that is spent in the functions. However, the first thing that you should have to pay attention to is that it took 50 seconds now. So no more 36 seconds. Things have gotten much worse. And come on. Yeah, the lesson is profilers add overhead. Everything becomes slow, even switching slides. Yeah. So now let's look in this report in the detail. So it does this thing. It says it inspected, 60 million function calls in this 50 seconds. And then it prints the table ordered by cumulative time. So on this side, you have the number of calls. This is total time spent there, time divided by the number of calls. Cumulative means it includes the time from the nested function calls. So in this case, you have the randint function that calls the randrange function, and this number includes that one. So that's what cum time is. And then it gives you the file name of the module, the line number, and the function that this time corresponds to. And surprisingly, you can see that most time is actually spent in the randint function. And that's, judging from the previous answers, that was not immediately obvious. So most interestingly, you will see in the code that this randint is used when you generate the original set, and then when you take subsamples of it. And the most time is actually spent in subsampling, so not in generating this huge original set in the first place. And the thing that you should learn from that is that your intuition is most likely wrong. So when you are pointing to a specific line and think, okay, that's the problem, most likely it's something else. And so you will spend weeks fixing that, and then this time will not be well spent in the end, because it turns out that the problem is somewhere else. But what I'd like to do now is to show how the visualization of this data works, because this report can get quite huge for large problems especially, and it's not immediately obvious if your program doesn't fit on one A4 sheet of paper what the real problem is. So to that end, I use KCashGrant, which is a tool designed originally for the Valgrind framework. It can take data from cprofile, albeit not directly. For that, there is a converter available, which also works on Python 2 and 3, called pyprof to calltree. You can give -o to cprofile to record the profiling data to a file. Then you can convert it from cprofile format into CashGrant output, and then run KCashGrant, see what's up. So I guess that's where the interactive part starts. What was it? I think it was 1. And right. So the resolution is not great, but if I increase it, I think you wouldn't be able to read it, so I leave it as is. So what KCashGrant shows you, basically, this pane is a square map, and it shows how much time is spent in each function, and the squares contain each other. On the left, it's the same kind of report as cprofile does. Also, you can here see the cumulative numbers in percents, and then at the bottom it has this text field. And basically, these two parts are symmetric. So it has a Kali map, which is usually the thing that is most useful. So it shows which other function calls each other, but it also has the reverse of it, which is the caller map. So it tells you which other functions call this function. But in this case, this is not terribly useful because this program is too straightforward. But if your program had loops and lots of different functions that might call other functions, then you might also consider that useful. And also same applies to cographs. So not many people actually know that KCashGrant can generate cographs from these files. And in this case, you see that there is the module confidence pi that contains the thing that is started. Then there is function main. Then there is this adaptive confidence interval function. And then times 10, it calls confidence interval. And this one calls randint and other stuff that it takes not so much time is just emitted from this code graph. And again, you might think this is not so terribly useful, but if your program contains a lot of structure, then this becomes interesting. So what you can see here, is basically the conclusion is the same as before. There is this confidence interval thing that takes 100% of time, and 70% of this 100% are consumed by randint. And the interesting part is here the source code tab. So you can click here. So what the function randint is, surprise, surprise, it's just a function called to another function randrange with a +1 parameter. So, and then let's go back to Kali map. So this is 70% and this is 54%. So you can see that function calls are not very efficient when there are millions of them. So just the fact that you call another function takes 20% of your time here. So with that, I think we can get back to the code. Okay, one other comment that I wanted to make is that you can get the same using a program called RunSnakeRun that also plots square maps. It can plot them directly from cProfile data, which is nice, but it's a little of a pita to install because it depends on VX widgets. And KCashGrant is usually available in your package repositories. So even though it needs a converter, I prefer it to the other one because then good luck installing it in a virtual or something like that. And then there is also a dedicated tool called gprof2dot that generates cographs. And this might be more interesting to you if your program has a huge intricate looping structure, and KCashGrant is very basic, but this thing, it basically generates the dot files that are then fed into GraphViz. And GraphViz is a graph visualization tool by AT&T Research, and it's very elaborate, so it's very good at coming up with layouts of graphs that look nice and are meaningful for different definitions of meaning. So if you are really interested in cographs, you can look at that. Okay, so whatever. Right, lesson number 6 is that visualization generally is a helpful thing. And then, anyways, now that we know where the time is spent, my suggestion is to speed things up a little bit, and we can do that by replacing the random number generator that I've been using that is in the standard library of Python by NumPy. So NumPy is a library that is designed for fast manipulations on arrays used all over the world by scientists and must be fast. So let's take the random integers function from NumPy and replace the standard library function with it. So I apply this changes to my program, basically 1 line and 2 imports. And the result is as follows. So I ran it through time again. You see that it takes 8 seconds now. The previous version took 36 seconds. That's quite an improvement. However, what I'd like to point your attention to is you know, these numbers are different now. So I changed the program. It runs much faster. The result is a little bit different though. So in this case, I can easily explain you why this happened. And the reason why this happened is because the states of the random number generators are initialized a little bit differently. And then when you use another one, even though it's also Mersenne Twister 1997, the numbers that come out of it are a bit different. But actually, in the previous version of this tutorial, this masked another effect. So I was young and naive and assumed that the functions that have the same name should generally have the same semantics. And so in Python standard library, there is this function randint. In NumPy, there is also a function called randint. However, the function from Python samples from closed range. The function from NumPy samples from open range. And therefore, this, of course, skewed the results. But because I didn't have any tests, I did not catch that. So that's the... And therefore, of course, I had to use the function random integers that implement the same semantics as in Python. So it samples from the closed interval.
Why don't we get a mean of 500? Sorry.
What, sorry?
So you get the mean 498 plus minus 2, something like that. Why is it not 500 if it's a random between 0 and 1,000?
You mean why my answer is not 500 here? So the reason is the sample is not big enough. And you know, it's like flipping the coin. You know that if you flip the coin, the probability of getting each side is 50%. But it can happen because this is so random that I will flip the coin 10 times and it will be always the same side. And it doesn't mean anything, but it just that I got so extremely lucky or unlucky if I bet on the other side. And same happens here. So of course, it is supposed in the limit of n be 500, but because my sample is just 100,000 numbers, and because of other things, like the whiteness of this empty generator is not so good and so on and so forth, it's a bit skewed. But I mean, in general, if I sampled much more, that would get closer, and then the confidence interval would also be, you know, becoming narrow and narrow. So now it's still, you know, there is some air here.
But it's not because it's picking 1,000 also? Is it, I don't know, closed form or open form? Or is it only going up to 900?
So closed is when it includes 1,000.
And does this include 1,000?
Yes. Yeah, but as I say, the number of samples is not high enough. And then I get this number, and then the confidence interval is also a bit skewed. But luckily still, I mean, these statistics are good enough, so it includes the right number at least. And this is what the confidence intervals are about. I mean, they should just include the right number. Okay, anyways, so that's what I wanted to point your attention to. The conclusion is that not all random numbers are exactly the same. Question is, can we actually do even better than that? And to see what we can do more, just, you know, rinse and repeat thing. And I have prepared already a second profile after this change. And what we see here is actually quite different. So you see now that the confidence interval is still the function that takes most time. However, the number that it takes to generate random numbers went down from 70% to just 20%. And then all other stuff shows itself now, like len is now taking 7% of the runtime. So it means already we've got quite close to optimal. But there is a huge gap here. So there is something in the confidence interval function that takes time. And this time is like 60% of the time. And it's not random numbers, and it's not any function that it is calling. So the question is, where does this time go? So I mean, in general, you would expect your things to be pretty filled up. So you have one function that takes time, and then another function that takes time, and does nested calls. But you don't have this huge gaps here which can't be explained. And we can't really go any further now because, I mean, assuming that I will take a different random number generator that takes, I don't know, 1% of the time, the improvement now will be I will just cut 1/4 of the runtime. So we need to understand what we can optimize in different ways other than just improving the speed of this function that it calls. Right, but that's all the method line profiling can do for you. So what we can't do though, we can turn to line profilers. So this is exactly this kind of situation where you have to dig a bit deeper. So how we use line profilers, we can install it via pip. Unfortunately, its record on pip is somehow strange, and therefore on PyPy, and therefore it doesn't install directly, and you have to give the URL. And it didn't fit on the slide. But I hope you will find, you know, everybody knows how to use Google. I hope. So assuming you have installed this thing, what you have to do, you have to make some changes to your program. You have to add this profile decorator, which is shown here in acid green, which is basically, I guess, not visible. But yeah, I'm sorry about that. And the reason why you have to add this decorator is because line profiling takes time. It's slow, and therefore you don't want to profile your complete program. You just want to profile this function that you are interested in, and then move on. So the function that I'm interested in is confidence interval. I add the decorator, and then I have to run the line profiler. When you install this thing via pip, it installs a script called kernprof.py, and this is how you run your programs. Or it's one way of doing that if you don't want to import modules and add more code. So my strategy is always to minimize the number of things I change in the program that I profiling. So I'm using this script. You have to give it -l, which says do line profiling, -o, save it to a file, and then you give the name of the script. One thing you can notice already, it took 90 seconds. So it takes now 10 times more, and this was like already the fast version. So it was the 8-second one. So line profiling is slow. If just profiling is slow, line profiling is very slow. But I mean, 90 seconds is still acceptable. So then there is also a bundled line profiler module. This module you can use to generate a report that is basically similar to what cprofile gives you. So here you have the annotated code of the function, line number, number of hits of every particular line, time it took per hit, % of time. And what you can see here immediately is that 90 whatever it is, almost 100% of the time is spent in these two lines in this function. And actually, you know from previous measurements that 25% of the time is spent in randint. And so if 90% of time is spent in this, or 100% of the time is spent in these two functions, it's something in these lines that is not randint, because this is just 1/4 of it. So these two lines are somehow a problem. Why is it so? Well, why is it not changing the slides anymore? Then I will get back to the computer. So in retrospect, that's actually quite clear what's going on here. And what's going on is you use I use the list comprehension. I generate a random number. I use these numbers first to create the indices in the original data array to subsample. So I generate a lot of random numbers. Then I have another list comprehension to create a permutation of the original data set. And then of course, this is not efficient because you could have replaced, or I could have replaced these 2 lines by just 1 line. So I could have used one list comprehension, so generate a random number, directly use it to subsample, and then of the subsampled values create a list. So I didn't have to actually, for other reasons than, I don't know, algorithmic clarity, put this on 2 lines. So now that it's clear that the problem is that most time is spent there, we can replace it and get a nice improvement.
Does random, can it generate the same number multiple times? Can you go backward?
Shh. So, right. I leave this question without answer for now. So we get a nice improvement. And the nice improvement is somehow expected. So we saw that these 2 lines are taking 100% of the time. We halved the number of lines. We halved the number of runtime. And, you know, the output didn't change. And this is a good thing because it shows that our program is still correct, or at least it produces the same results as before. The reason for it is that the random numbers are generated in the same sequence, and there is still the same number of numbers generated. Therefore, there is nothing that has to change. And 4 seconds, it's already a nice improvement over 36 seconds, I must say. So conclusion is method line profiling is maybe a default go-to thing, but sometimes it shows you just one huge gap, and you don't know where the time is really spent, and therefore you have to use something else. And then the question is, can the same insights be obtained faster? Because as I showed, 8 seconds it took to run the program, 90 seconds it took to profile it. If you have a program that runs half an hour or 1 hour, it will take 30 hours to profile it. And this is not, or what is it, not 10 hours. 1 hour times 10 hours. But this is still like more than a work day. So you start it when you come or when you leave, and then next day you come to see the results. And of course we can't do this. This is what the statistical profiling is that I mentioned in the beginning. StatProf is a very nice script. It can be installed with pip directly. So the reason why it's faster, to repeat myself, it's because instead of instrumenting every single line, it just adds a trigger. Every time this trigger is hit, it looks at the stack and records where we are in the call stack. And therefore, statistically, you will spend, when you wake up and look at the stack, if something is long running, you will statistically spend more time in this function. So to use StatProf, you have to modify your script a little bit. You have to import StatProf for starter, and then there are functions startprof stat and startprof stop. So they start the measurement and stop the measurement, and then there is a function to display the results. So don't worry. I mean, you will get all these files at the end. So if you can't see this, especially at the back, it's not so tragic as it looks like. So here, that's what I'm doing. I'm running again this file now without any fancy imports or anything, and StatProf prints the summary. So first, it took 8 seconds before. It's now taken 9 seconds. So that's a very, very small overhead. And you get basically the same result. So in these columns, you have percent of time, time in seconds, and cumulative and spent just in this line. And these times are estimated, as I said, by looking at the stack, and it realizes that most of the times when it wakes up, it spends time on line 43 in function confidence interval, and then a smaller proportion of time on line 44. So these are not precise results as with line profiling, but I mean, basically what do you want? You've got almost the same information, and you just spent 1 second of extra runtime. So this mysterious lines 33 and 43 and 44 are these two. So, and then basically you replace it and then you go on. And now I want to switch gears a little bit and talk about memory usage. So before I have been assuming that CPU time is the only thing that matters, but RAM usage often, or in also equally often in the case of my work, when the compute nodes have just a small amount of RAM per CPU thread, can become a problem. So the default go-to option, as I said before, is to use memory profiler, and I'm not going to show it. And the reason why is because it works exactly in the same way as line profiler. You add a decorator to your file, you run your program with memory profiler module, and then you get a report. Unfortunately, it's very slow and not always helpful. So the reason why it's very slow is because it's looking at the every single line, and then it checks how much memory the process is using, and it does this by default by forking PS and parsing the output of PS. And you know, when you fork something, every single line in your code, this takes time. Therefore, people install something called PSUtil, which is able to get the same information via, on Linux, I think it's via the proc file system. So not through the system calls directly, which would have been nice, but at least it's not forking, you know, every single line. But still it's slow. And anyway, so if you want to use that, the take-home message always install PSUtil. Otherwise, you will wait till the end of your days. So I have prepared a sample report, and you see that I didn't lie. It's exactly the same like line profiler, and it took me in this case 40 minutes to generate that. So I basically started it and went for lunch. That's what I mean by slow. This is 40 minutes to profile an 8-second program. And okay, I mean, the problem is, of course, that I have a tight loop here, and it's a bit extreme case, but nevertheless, that's the order of magnitude of slow. And so what you see here is memory usage in one column, and the other one is the increment. So it goes line by line, checks the memory usage. Here it does many iterations and averages them. And you can see that basically at the start of the function, always the memory on average is 29 megabytes. And then when it gets inside this for loop, the memory consumption grows, and then it returns. But so good news, you have no memory leak here, but it's not exactly clear where this memory have gone, and how do you go about fixing it. So it gives you that, you know, the problem is in this region again, but it doesn't, or at least for me, it's not immediately clear what do you do next. And so therefore, I'd suggest to do something more interesting. Let's look at how we use Massive, which is part of this Valgrind dynamic translation framework. Usually, at least among my colleagues, it's considered to be something very scary, but it is not, as a matter of fact. And I will, so what Valgrind does, it's something like a virtual machine. It basically decompiles your code into the internal representation, and then it can apply transformations to it. So one crazy guy even wrote a plugin for Valgrind that translates instructions from one CPU instruction set to another, and then you can, I don't know, run power things on 86. But of course, it is particularly useful for correctness checking and performance analysis. And from this description, you might have gotten an idea that this is something very low level and must be also terribly slow. But again, these rumors are widely exaggerated. So another thing to mention is that Massive actually generates cryptic text files. And the key to using it productively is visualization. There is a project called Massive Visualizer, which is an extremely useful tool. However, unfortunately, no distribution that I know has it in the package manager. So you have to build it from source. On Ubuntu or Debian, it's enough to install Build Essential, CMake, and KDLibs that encompass all the dependencies. On other distributions, if you are running Arch Linux, you don't have to. I don't have to tell you what to do. So you just clone the source code, create a directory, build directory. This thing is how you tell to change the default prefix in CMake. So this is especially for AutoTools haters. So take that. And then, however, you can just simply run make install, and then it works. So in order to use Massive Visualizer, first you have to generate a trace with Vagrant. You call it this way. You tell it use this particular tool. What you can see immediately, it starts printing these numbers. These numbers are process IDs of the child process that is being examined. There is some licensing blurb and so on and so forth. It says Massive, a heap profiler, and you can see that it takes 100 seconds. So it's at the, the slowdown is at the level of line profiler. So you had whatever 10 seconds program, you profile it in 100 seconds. So this is a lot, but it's much less than you would expect, considering, especially if you read the Vagrant source code and know what it's doing. It's amazing. So it generates this crazy text file, which is human readable for if you are in the subset of Vagrant developers. It postfixes it with the PID of the program, and then you usually use the visualizer to see what's really going on. So yeah, let's see how it looks like. Oh no, here. So it was this PID. Yeah, and that's actually very nice, and it looks even nicer if you use a dark theme. So unfortunately my Qt theme is not dark, so otherwise you can look at these graphs like a little hacker. So what you can see here, this is the memory consumption chart. Time in steps. Massive runs your program and periodically takes samples, and then it records the breakdown of which functions at that time allocated how much heap memory they were using. And to interpret this chart, so first, of course, you can conclude that this process used, what is it, like 13 megabytes of memory or 12? No, so peak is at 11.3. So not so much, but to get really useful data, you have to look at the breakdown. So you can see here that this function pi_int from long, the red one, used the most, like 4 megabytes, and then another function, pi_list append, used 2 megabytes, and then the rest was pretty much not so substantial. And apparently you can also see the garbage collection cycles in this these peaks here. I mean, at least that's how I would interpret that. But to understand really what it means, you have to know something about low-level Python C API. So pi_int from long, what does it do? So you have to know that in Python, everything is an object. Even numbers like integers and floating point numbers, these are all objects. And this means, like in C, you allocate an array. These are just, packages of pieces of 8 bytes or something like that, ordered in a particular sequence. In Python, if you create an integer, you allocate this 8 bytes, and then on top of that, you allocate a lot of other things to provide this Python machinery and slots and whatnot, and then it becomes this Python object. So in order to actually create an integer, you have to take a C long, and then this function pyint from long creates a Python object out of it. So this is also otherwise called boxing and unboxing, when you convert from Python object and to Python object. And PyListAppend, what this thing does is when you are building lists and appending elements to it, at some point, I mean, it doesn't know in advance how much memory do you need. And therefore, when you do an append, if there is not enough pre-allocated memory, it allocates more. And therefore, you see in this trace this growth of the list as this memory was allocated by PyListAppend. So these things actually already kind of give you the answer what's going on here. The problem with this code is that I have this list comprehensions to generate the samples. So what this does, it generates an integer using NumPy. In NumPy, on the low level, it allocates a normal C value. Then this value is converted to a Python object, and then it is used to subsample as an index from a list to create a Python list using a list comprehension, but under the hood, it still calls PyListAppend. So first is, or the first problem is that instead of allocating the whole batch, I generate these numbers one by one. Second problem is that I create these lists and I use Python lists instead of NumPy arrays. So NumPy arrays are highly memory efficient structures. So it has some 50 bytes of overhead or something like that, this ND array. But once this has been allocated, the numbers in the NumPy array are just like in C arrays, contiguous blocks of memory, and they don't have all this extra Python machinery attached to them. So it is advantageous to use NumPy arrays throughout first, and then allocate large blocks at a time. And so, unfortunately, this was already mentioned some time ago. So what I could have done, instead of doing this list comprehension, I could have actually given a size argument to NumPy rendint and tell it, OK, generate a batch of 100,000 random numbers. And then this would do it inside NumPy with a loop at C level and create a memory-efficient Python NumPy array instead of a Python list. And then I could also do the same here. So instead of sampling this way, there is a function in NumPy called choice, and it allows to sample with replacement from a NumPy array, and you can tell it how big the sample should be. And so again, this whole thing can be pushed from Python level to C level by vectorizing the code. So once you do this obvious changes, you can start the visualizer again, or actually it supports tabs. So let's just open it in a different tab. And you'll see something like this. So what you can see here immediately, the total memory consumption went down from 12 megabytes to 7 megabytes. And these functions here are, they are basically gone from the list, because you are no longer boxing and unboxing numbers like crazy, or allocating and reallocating lists, but you directly allocate a large block of memory, fill it with numbers, subsample from it, fill it with numbers. Very efficient. And this function that now tops the list by array new from desker int, it's actually a function that belongs to NumPy C API. And well, I'm not sure if you can see it here, or if I can No, it doesn't want to shrink. So basically, this is the thing that does the random number generation. So inside it calls empty rand. So of course, if you are now familiar with NumPy CAPI, maybe you can think of some more improvements. But otherwise, it shows that like the low-hanging fruit have been picked. So this was an obvious problem. Now this problem is gone. So yes, the conclusion is then Valgrind tools are very useful, and they are useful even if you are looking at programs, at Python programs. So again, there is this myth that in order to use Valgrind, you have to have this worn-out sweater, shirt, and then long beard. This is not necessarily the case. So the reason why I'm not showing other tools is because Valgrind is almost like, works the same way as cProfile. KashGrant you would need if you were Francesc Alted. I think he's not here. So this is the guy who develops NumExp, which is an evaluation engine for Python. And what this thing does, it tries to make numerics in ways that are friendly to the CPU. So it will optimally fill the CPU cache with numbers and then do great things on them. And for that, he has, of course, to check that what he is doing is efficiently using the caches. So he, as a Python programmer, uses KashGrant. Okay, anyways, so at this point, what we have done is we have sped up the function by factor of 6 or more. Memory consumption has been reduced by 30%. And this all was done by changing 3 lines. So unfortunately, none of you suggested at the beginning, because the previous time I've given this tutorial, people were picking on me regarding this mean function. So just a moment, right? And they were saying mean function in Python, that should be very slow. But as a matter of fact, you have seen that we haven't even got to this point where this is a problem. So just 3 lines of code, yes?
So did you time the last version of your code? Because now that you replaced this comprehension with this millions of calls of random,
Yeah, okay, I cheated a little bit, so it became slower. So it's 6 seconds. Before it was 4 seconds. But I mean, you'll see in a moment what happens then. Right, anyways, so point is 3 lines of code that needed to be changed, and just try to think of how much work it would have taken you if you would be doing this by guessing. Right, anyways, not bad. Now, the question is, can we improve things even further? So, for instance, we have replaced this comprehensions with NumPy calls. It might seem so, and it got more memory efficient, but a bit slower. It might seem like there is no work left to do. However, at least by 1 order of magnitude, you can improve it by changing 2 more lines. So that would be your homework. So this whole thing, if you don't want to retype the code or copy-paste it from PDF, are available at this URL. I'm not sure how long it will stay there, but last time, not sure meant like more than half a year. So, and also this is in the PDF. So if you open the PDF, then you have this link already. And I will later get back to this slide. So if you don't manage to write this down. So with that, I think I'll get to the conclusions. And first things to summarize are my statements about benchmarking. So what I can't repeat enough is use standard tools, and in particular time it. And I hope I have convinced you that time it is worth it. So you can see that it tries, for example, to minimize interference from other processes by assessing how fast or slow your function is, and then do an appropriate number of loops. Usually, homegrown decorator writers do not get that far. Time is very interesting tool. There is something that I didn't tell you about. It has a -v k, but I think to interpret this output, you would need to go to the next tutorial. The other thing is you have to be aware of the interference at all levels. So these all numbers that I have shown you that I run on my laptop, they are so very nice only because first I disabled Turbo Boost, I switched off CPU frequency scaling, and I stopped cron daemon that was launching periodic jobs in the background. Because what happens very often is that your CPU scales up the frequency to compensate for increasing load, and therefore you run your program, it takes some seconds, and it runs slowly, and then the CPU is, the frequency is scaled up, then you run this program, it runs much faster without you doing anything. Or conversely, you have a program, and then you have a cron job in the background that just kicks in, and it runs slower for unclear reasons. So at one of my workplaces, there was a case that towards 4 o'clock, computers would uniformly get slow. And the reason is that there was a policy of the computing center to do TSM backups. And it was expected that people are kind of leaving work or doing email at that time. So, and nobody knew why this was happening and was not under their control. Or conversely, at the other workplace, the computers were slow in the morning. And this was because there is this mlocate library that is being built on this cron job to build the mlocate library that indexes NFS shares, launches when like some minutes after the computer is started, and then the computers of the whole department would hit NFS server with indexing requests, and things would be slow for half an hour. So these things, they bias your results. And then hot hold caches, I have shown you on the example of this dictionary. So when the cache was hot, it was very cheap to pull things from it. When the cache is cold, you have to actually compute things. So then, as time it does, repeat the experiment several times, make sure that the numbers you get are consistent. And the conclusion that I would make actually is counterproductive. So because benchmarking is hard, avoid it if you don't have to do it. And then, this is also a recurrent story in my field. People all the time publish papers with the benchmarks done wrong. And they are so sincere, they don't even understand that they do it wrong. And that's annoying to deal with them. So I don't know why they are all so obsessed with benchmarks if they don't know how to do that. And with respect to performance optimization, again, I hope that I was trying to get this point across, that your intuition doesn't necessarily point you to the source of the problem. So you should really approach the problem in a principled fashion, thus run profiling, and then don't trust your intuition. Surprisingly, app and system level profilers can be surprisingly useful. So Valgrind is very low level or high level, depending on how you look at it. It helps a lot though. Time is very simple. It's very helpful. There is another thing that I mentioned at the very beginning called perf, which is also quite useful. Tomorrow, I think you will get a more detailed account on how to do that. And then there is this law of diminishing returns. So you have to know when you have to start profiling, but you also have to know when to stop. And this is, I guess, my personal problem. I don't know when to stop. So I profile for weeks, trying to squeeze every single bit of performance out of the code. But then in the end, assuming you are working, in a business that provides a web service that has to have a guaranteed response time of 1 second, it doesn't really matter if your thing completes in 50 milliseconds or 5 milliseconds, as long as it's below 1 second, your business goals are met, and this optimization that you spend your valuable programmer time on is, maybe it's fun, but it doesn't benefit your employer, really. So often, small performance improvements, like 10% performance improvements, take 90% of your time. So just pick the low-hanging fruits. If your business goals or scientific goals are met, just forget about it. Get on to the next thing. Then the other cautionary tale is profiling adds overhead. And maybe I didn't scare you enough, but then when you have production scenario and you want to profile something, and you want to profile something because something is slow, and then you turn on profiling, and then it becomes super slow, and then the whole system melts down because your server was overloaded already because things were slow. Now they are running even slower, and then it's dropping the request at even higher rate, and then everything collapses. So don't just import cprofile in your live copy, which will be immediately picked up by the application server, and then you'll collapse your whole infrastructure. And finally, I think it's very important to follow some methodology. So I'm not going to get into the methodology wars, but this Brendan Gregg guy, whom I've mentioned already before, have written extensively on this subject. And it's helpful to use some principled approach. So on this webpage, which you can check later, he has a bunch of anti-methodologies and methodologies without anti. And yeah, I think it's really helpful. And now, yeah, basically I have to wrap up. First off, I would like to acknowledge you for eventual feedback. It's really helpful for me to know especially what's wrong with what I'm doing so that I can improve later. Then, thanks to TR Jordan, this was the guy who gave me this idea of using the confidence interval thing as a test case. The reason why this problem popped up is because they were developing an elaborate monitoring system, and they wanted to see somehow if it's possible to detect changes in the state of the system semi-automatically. And therefore, they tried to detect the peaks in performance, but it was not clear how much was the confidence in that the state of the system was changed and the operator has to be alerted. And so, yeah, this is where this comes from. And then Brendan Gregg allowed me to use his illustrations. Ian Oswald is someone who I like to acknowledge for good ideas. So in this talk, I was basically trying to show you how to find the problems and not so much how to solve the problems. And the reason for that is that we agreed with Ian that his tutorial will be more like on solving problems that you have found using the ecosystem that exists in Python to solve various performance issues. He has, so he hadn't paid me for it, but I have to plug in the advertisement for the book that he's just released. I think it's a really good one. It's called High Performance Python, I think. And I'm sure he'll also mention it during his talk. All right, and finally, conference organizers for having me here, you for listening. Thanks, everybody. I'm not sure if I have time for questions. But anyways, I think the next talk was canceled or something like that. So you can find me here and kick me or, give me a orange juice. Or
I have a question. Where can we find this beautiful presentation?
Well, what, sorry?
Where can we find this beautiful presentation?
Oh, this is very easy. Ooh.
Are you sure?
Here. So this archive contains everything you ever need. So you have the presentation, you have the source code, you have the snippets, the profile traces, so that you can play with them. So use it. Yeah, so.
Is there something similar like line profiler for Python 3?
For Python 3?
Yeah.
So line profiler, that is this beta 3 version, I think is not working with Python 3. However, there is a fork on Bitbucket or GitHub that is working for Python 3. So you can't install it via pip, but I don't remember the link. It's either on GitHub or Bitbucket, and so it's there.
Okay.
And same is for StatProf. So StatProf, also there is a fork that supports Python 3, and PyProf to call tree thing I have patched myself, and now it's also in the PyPy. So this works out of the box. Yeah. Yeah.
Do you know any statistical profiler that is able to profile C compiled extension in a Python notebook to have the stack trace, the stack of the Python calls and the C calls inside?
Well, I think so. Squappy, for example, can't do this. So this is so I'm not so much familiar with C infrastructure, but in HPC, you know, there is a bunch of tools for profiling and performance analysis, and these tools can be basically subdivided into groups: things that produce data, things that analyze data. And one of the very popular collectors is called Score-P. So this is something that I mentioned at the very beginning. No? Yeah, so it's this thing. And this collector, you can instrument your program, and I think it can collect both statistically the information and maybe also deterministic fashion. And then there is something called HPC Toolkit, and this is a statistical profiler for C. So, and these things produce data. This data you can analyze using, for instance, Scalaska, which complements Score-P. But I don't know, maybe there are other options, but I'm just not very familiar with the field. So, for example, Intel Vitune Analyzer, I think, combines both things. But yeah, you'd have to ask someone who is current with the C stuff. Okay. Yeah, I guess we'll have to close it now. Yeah. So just find me if you have comments or questions or anything.